All right, so what questions do you guys have from Unit 2? What kinds of things do you want to go over, Dave?
Like an object is being pulled in two different directions and it has or something.
Okay, so like something being dragged and friction's resisting, or something actually being pushed in two different directions?
Two different directions.
Two different directions, okay. So. This is a 60 kilogram box. We kind of need that number. Okay. I tried to use that E twice. I was being really lazy. Do ask. Do east. Okay, so we're looking for the acceleration of this box being pulled by two ropes along a frictionless surface. Okay? In all Newton's second law questions, what's my first step?
Free body.
Exactly. I got to draw a free body diagram of this situation first. Okay? So I have a 60 kilogram box being pulled due east by 200 newtons worth of force. Okay, and we'll say that's 50 degrees. Okay, north of east with 300 newtons worth of force. So there's my two forces. That's my free body diagram. Other than kind of showing my givens, that diagram's pretty useless. Okay, other than it shows where my two forces are. Okay, what do I need to do with the two forces on that diagram? I have to draw another kind of diagram. Okay, let's think about it this way. Which way is that box going to go?
East.
A little bit east, but also a little bit, yeah, north. A little bit north and a little bit east. Okay, we know that because if we logically put these two vector quantities together, okay, that would be our vector diagram, right? Force is a vector quantity. Net force, which I need to get acceleration, is the vector sum of all forces. So this is no different than a question from Unit 1 where I'm asked to find the displacement from two displacement vectors. Okay, I have to put these two forces together for the logical product of those two forces, which, as everyone said, is a northeasternly directed acceleration. Okay, so my overall resultant in this question isn't displacement, it's F net. Now I'm drawing it this way just because I don't want to overlap my other lines. You could very easily draw it along these other lines, but it gets kind of confusing when all the lines overlap, so I'm drawing it this way. Okay, so this would be its x component, this would be its y component, and that would be its direction. All right, so to start this out then, because it's now a vector addition question essentially, the x component for my first vector is 200 newtons east. The y component for my first vector is 0 newtons. Okay, it's straight east. Doesn't have a north or south component. All right. For my second vector, okay, I have an x component that is the adjacent side, so it'll be the cos of 50 degrees times 300 newtons. Sorry guys, I didn't fire up my calculator. Take a minute here. Okay, so we're looking at 192.84. I'll keep all the decimals, obviously. Newtons east, and then my north component is the opposite side, so sine of 50 degrees times 300. 229.81. Newtons north. Okay, so what do I do next? It's a good review of vector addition at the same time. I found all my x's and all my y's. I need to green pen next. What do I have to find? What was the whole purpose of finding all those x's and y's? Yeah, well, I need to find f net, but f net's triangle has a y and an x in it too, right? Okay, would its x and y components be the sum of all the x's and y's here? Okay, that's my next step then. Okay, vector addition, right? To get the green x, I'm going to add the 200 newtons here to red x. That will give me the full x component that I see along the top. Okay, because if I had drawn this the other way, right, that would have been my x component right there. Right, so those two added together will give me my resultant's x. So 192.84 plus 200. So I'd write 200 because that makes sense. 392.84 newtons, okay, will be my overall x component. And there's only one part of this where I go north. So green y is equal to red y. Everybody okay with that? All right, so that'll be 229.81 newtons. Okay, so this one's east, that one's north. Okay, now that I have those two, what do? I do Pythagorean theorem. That will get me the magnitude of my net force. Okay, so when I do that, obviously with all my decimals. I love having this new calculator. Oh, except that I forgot to put a plus in there. Screwed up something. It squared my square root, didn't it? Yeah. Okay. I take back what I said. I don't really take back what I said. Okay. This number squared plus that number squared. That's better. Okay. So my F net is 455 newtons. I only have two significant digits though, so I'm going to say 4.6 times 10 to the 2 right now. Newtons, but now I also need the direction because F net is a vector quantity. Actually, sorry, I don't want to do that yet. I have one more step after that. Whatever. I have the decimals in my calculator. Okay, so theta is going to be tan to the minus 1, okay, of For me, the way I drew the triangle, it'll be the 392 over 229, okay, opposite over adjacent for me. Okay, so I'm getting an angle here that is 59, actually it'll be 60 degrees because I have only two significant figures, 60 degrees east of north, okay, which makes sense given the numbers that I had. Okay, so 60 degrees east of north. Now, what do I need to do with my F net? Because the question wanted the acceleration. Alright, so we got to quickly review this. Net force is mass times acceleration and the vector sum of all forces. So I just did the vector sum of all forces. It's 455 newtons. I want acceleration. What do? Divide by m. Okay, guys, I'm a little concerned that we're drawing a blank on that step. Okay, that is the heart and soul of Newton's second law. That is definitely got to be something to review here over the coming week. Okay. All right, so we divide that by our mass, which was 60 kilograms. Okay. Back up and grab that. That was my net force. Okay, divided by 60. All right, so the acceleration is going to be 7.6 meters per second squared at 60 degrees east of north, or at 30 degrees, all right, north of east. Okay, everybody all right with that? Okay, what else do we want to go over? What other questions might we have from Unit 2?
The one with the sign.
Okay, a static question. Okay, I have a 100 kilogram sign, okay, and it's hanging from these two cables that have an angle of, let's say, 120 degrees between them. I want the tension in each cable. Spoiler alert, it's the same for both cables because they share that common angle in the middle. I'm going to give you guys a minute to think about that one. Okay, so as we were saying, the key thing here we have to realize is that the net force is 0. The sign is not moving, okay? So that means the force upward on the sign is equal to the force downward on the sign. So we might as well start by making a free body diagram where we calculate that force down, okay? That force down is the force of gravity, which is m times g, so that'll be 981 newtons. All right, now, there are two forces pulling up on this lamp or sign, 100-gram ball, okay, a 100-kilogram ball. So what I have to do here is essentially find those two forces, okay? So those two forces are here and here, okay? Now, since this here was 120 degrees, this angle here must be 30, okay? Same as this angle over here. You could have also drawn this up the middle. I'm just separating the two forces, okay? Because I find when people draw the force up the middle, they draw it as 981 newtons, which is right, except each one of these cables is only holding half that much. Okay? If both those cables have an up component of 981 newtons, this thing is flying upwards with an acceleration of 9.81 meters per second squared. And that is not happening. Okay? So each side is 490.5, half of 981. Okay, so now I have the upward component of the tension that I'm supposed to find, this cable here. Now that I have that side and the angle, I can find the hypotenuse. I don't even need to find this side, it doesn't matter. Okay, so to find the tension, okay, I'm going to use trig. The sine of 30 degrees is going to equal the opposite side, 490.5, over the hypotenuse, which is the tension I'm trying to find. Everybody follow my trigonometry there? Okay, so to isolate t, I'm just going to cross multiply here. So t is going to equal 490.5 divided by the sine of 30. Now this is probably what messed people up. They didn't like the answer they got when they did this. What answer did you get? 981 newtons, right? And everybody looked at that and went, oh no, it can't be because its downward force is 981 newtons. Remember, that's an angled force. It's just because I picked a really bad angle off the top of my head. Okay, that it worked out that way. Okay, but yeah, that is supposed to be 981 newtons at 30 degrees above the horizontal or 60 degrees from the vertical. Okay, it's not straight up. Okay, the straight up force is half of that. Okay? But because we got a 30-degree angle in there, the hypotenuse is twice that side. This happened actually on your assignment. Same thing happened on your assignment. A lot of people didn't like that they got the same number as their weight. Okay. What else? Oh, sorry, did I need to leave that up? Yep. Okay, what other kind of questions do we want to go over?
Did you do a work energy theorem?
A work energy theorem question, perfect, okay.
Is that 100?
Yeah, 100 kilograms inside there, yep. Okay, so I still have to put more stuff on here. This is just where we're starting. Okay, we've got a 100 kilogram mass at the bottom of a ramp. Okay, at the bottom of the ramp, it's moving at 3 meters per second. Okay, it gets dragged up a 20-meter long incline. Okay, by a force of, let's say, 150 newtons. Hang on, I gotta calculate if that's gonna work. It is not. Okay. Now it will. Okay, so now it's being dragged up by a force that would actually drag it up the ramp. That force was not going to cut it. Okay, so it's being dragged up the ramp by a force of 500 newtons. Okay, when it gets to the top of the ramp, it's 10 meters higher than it was at the bottom of the ramp. I want you to calculate how fast it's going at the top of the ramp. Okay, this is a work energy theorem problem. Okay. And the box is being accelerated up the ramp. That means it's going to be going faster at the top than it is at the bottom. Or at least it should be if I calculate it right in my head. The ramp's frictionless. I didn't mention that, but it is. Okay, give you a few minutes to think about that one. All right, so the energy's changing here. This is not a law of conservation of energy question where the energy at the bottom and the energy at the top are equal. There's a force being applied here. Okay, this thing is being pushed up the ramp. So what I need to say then is that work is going to change the mechanical energy of the box. Okay, what that's going to look like is this. There's a force being exerted over a distance, and when we're finding change in mechanical energy, that's going to mean my final kinetic plus my final potential minus my initial kinetic plus my initial potential. Right? That's change in mechanical energy. Now, I need to do a little work here right now, okay, in that, well, I don't really need those brackets, but, okay, I'm trying to find something that is part of my final kinetic energy. Agreed? All right, so what I want to first do is bring this stuff over to the other side by adding or subtracting? Adding, okay. So I'm going to do that first, and I'm going to have force times distance, okay, plus essentially my initial mechanical energy. So I'm just going to write that out actually as formulas here. 1/2 mvi squared plus 1/2, or sorry, not 1/2, plus m times g times h, initial. Okay, that's going to equal, okay, sorry, those are supposed to be, yeah, initial. Okay, equals our final, that'll be 1/2 mvf squared, okay, plus m times g times hf. So what do I need to do with the m times g times hf now? Remember, I'm looking for this. What do I do with mghf? Subtract it, yep. Okay, so here's what we're saying. The work plus the initial energy minus the final potential should give me my final kinetic. Okay, we're saying work plus the mechanical, plus what we had to begin with, okay, those two things added together, subtract the final potential should give me my final kinetic energy. Okay, that's what we're saying at this point. So force times distance plus 1/2 mvi squared plus mg hi minus mg hf equals 1/2 mvf squared. All right, I'm looking for vf. We're going to do it the half and the m. Divide them over. All right, and then I square root. That'll give me vf. Now, this is as tough a one as we ever did. Okay, the one that's on your finals, not this time. But I thought I'd show you one that's got everything in it, just so you see it all. Okay. So I'm going to have the force, which was 500 newtons, times which distance, 10 or 20 meters? Which distance does the force act over? 20. Okay. Plus 1/2 times 100 times, was it 3 squared, plus 100 times 9.81 times 0. Don't even need to have that in there, okay? Because my initial potential is 0. Minus 100 times 9.81 times my final height, which was 10, okay? Divided by 1/2 times 100. Okay, that should give me VF. So we got 500 times 20 plus 0.5 times 100 times 3 squared plus, no, sorry, minus 100 times 9.81 times 10, and I don't think I put enough brackets in here. Okay, 1,000 by 10,000. Okay, so at the top of the ramp, it's moving at 3.6 meters per second squared. So did it change its speed by very much? No. The reason for that is it would have taken 490.5 newtons worth of force just to move it up the ramp. Okay, that at a constant velocity, it would have taken that much. Okay, that's why when I first put the 150 up there, I went, wait a minute, that's not going to work. Okay, so of course, it's not going to change its velocity by very much. I only have a net force here of 9.5 newtons changing the kinetic energy over that 20-meter length. Okay, now on your test, I've made it a little bit easier. Okay, on your final exam, you only have one type of energy that's changing. Okay, so you're only changing either kinetic or potential, which would make this question a lot easier. Okay, you don't have to worry about potential at the top, potential at the bottom, and kinetic at the top, kinetic at the bottom. Only one type. Okay, what else? I have a request. Can you do my request? An inclined plane? Okay. I'm surprised nobody asked about that. I'm actually a little bit hurt. Okay, I'm feeling like you guys don't hear me. Okay. Okay. Okay, sliding down the ramp at 1.7 meters per second squared, so it's accelerating down the ramp. Okay, it would accelerate faster than that if there was no friction. Okay, so there is friction, and I'm asking you to calculate what the force of friction is. All right, so I'm gonna give you a few minutes, and then I'll put the forces on there, and then give you a few more minutes to try and solve it. Okay. All right, so with all inclined planes, gravity acts straight down. Okay, so there's our force of gravity. Okay, this side here is normal force, but that's going to be completely unimportant for this question. Okay, and then this side here is our force parallel, and then this here is 30 degrees. Okay, so when we're looking at this, F parallel is the one that's going to pull down the ramp, and what's going to resist it up the ramp? Force of friction. Okay. Now, right now, without doing anything else, can I calculate the net force acting on the box? How? M times A. All right, so I should do that right away, because I'm going to need that. Okay, so F net equals M times A, 200 times 1.7, so 340? All right, so 340 newtons down the ramp is my net force. Okay. Next thing I got to calculate is F parallel, right? Because I can calculate that as long as I calculate FG, right? So FG, okay, 1,962. Sorry, I put a 0 on there that shouldn't be there. 1,962 newtons, okay, is my force of gravity acting down. F parallel is the opposite side to the 30-degree angle, so it's half of that. It is 981 newtons. See, I picked numbers where I can just do the calculations in my head. Okay. All right, so my force down the ramp is 981 newtons. My net force, which is the sum of F parallel and the force of friction, is 340 newtons down the ramp. How do I calculate F? Exactly. Okay, F net is also the vector sum of all forces. That means it's F parallel plus the force of friction. So if I want to calculate the force of friction, I'm going to subtract F parallel here. So 340 newtons minus 981 newtons is going to give me my force of friction, which is going to come out negative because I made down the ramp positive, and so that's okay. All right, so 340 minus 981 is giving us negative 641 newtons. So it's 6.4 times 10 to the 2 newtons up the ramp. Okay, so that question makes us do a little tiny bit of vector stuff. Okay, makes us do m times a, makes us do sum of all forces, right? As every Newton's second law question would do. Right? Now, another thing we talked about during that unit, we talked about systems. Okay, if you have a system and the whole system is accelerating, okay, the net force then acts on all of the mass. Okay, so let's say we have, sorry, can I go to the next thing? All right, so let's say we have a situation like we had in our lab. Okay, so we have a pulley, that's a pulley. Okay, and we had the cart here. All right, so the cart was attached over the pulley to a hanging mass. Okay, so let's say that the cart has a mass of, I don't know, 2 kilograms. Okay, and the mass that's hanging over here is 0.750 kilograms. And let's say there's a force of friction acting here of sorry, I'm doing calculations in my head again. $40 newtons. Okay. What is the acceleration of the cart? Okay. I want you to calculate the acceleration of the cart given that information. All right. Give you a few minutes on that. Okay. So the other force that's acting here is the force of gravity pulling down on the 750 gram mass. All right. So I'm going to calculate that next. 0.75. Okay, times 9.81. Oh, I screwed up big time, didn't I? That was stupid. I was thinking it was 7.5. So it went backwards. Friction pulled it that way. All right, I'm going to change a number here because I had in my head not 0.75, but 7.5. When I put the 40 up here, 4.0 newtons makes way more sense. Sorry about that, guys. Okay, so 7.35. 7.5, right? Okay, so I got force of gravity acting this way. I've got force of friction acting this way. So if I simplify this diagram to represent the whole system, it looks like this. Okay, that's what we've got. The whole system has a mass of 2.75 kilograms, and the forces acting are this 4 Newton force and this 7.3575 Newton force going the other way, which means my net force is going to be 3.3575 newtons that way. All right, now I want to find the acceleration of the cart. So acceleration is F net divided by m. So 3.57, sorry, 3.35 newtons divided by what? 2.75. Remember, that net force is accelerating the whole system. That's the trick. two systems. Okay, whenever you get the net force, you have to divide it by the mass of the system in order to get the acceleration of any part of the system. The only thing that we can add to this that's unique to the 2 kilogram mass is its direction. It's accelerating to the right, okay? Whereas the other mass is accelerating down, okay? But their accelerations are going to be the same because they're attached, and all parts of the system have to behave together. Okay, so 3.3575 divided by 2.75. All right, so the acceleration of the cart will be 1.2 meters per second squared right. Okay. All right, what else would you guys like to go over? Good. Not going to be on the test. Okay, you're not going to have one of those 2 boxes pushed by a hand kind of questions. Nobody likes those. You still have some Newton's third law stuff on the test, okay, but it's not a problem like that. It's like multiple choice stuff, checking your understanding, like the mosquito question on your unit 1 where it's splattered on the windshield, right? Okay. So yeah, you'll have some stuff like that, okay, but no, you're not going to have a 2-box question, okay, on your final. You're welcome. See, now some of you, see, because I saw you do that, right?
Yeah.
So you make the sign across. That reminds me, our old principal who was here before Mrs. O, he used to have a saying that he would remind everybody of right before finals. And it was very wise. He always said, study like you haven't prayed. Pray like you haven't studied. See? That was your answered prayer right there. See? Now you have to do the other part of it, study like you haven't prayed. Okay. Now you're good. Okay, you got your prayers answered, now you got to study. All right, what else do we want to go over?
Conservation and mechanical energy.
Okay, conservation of energy question? All right, this box is sliding down a frictionless hill. Okay, frictionless hill. And at the top of the hill, we don't know how high it is, but it's moving at 4 meters per second. And a little while later, it is now only 10 meters from the bottom, but moving at 16 meters per second. Tell me how high the hill is. Okay, so since there's no friction, energy is conserved. There's nothing to lose energy to, so the energy at the lower point is equal to the energy at the higher point, and that's how we start this off. EI equals EF. Okay, and so that's going to mean m times g times h initial plus 1/2 mv initial squared equals m times g times h final plus 1/2 mv final squared. Okay, and so we are looking for hi. We can cancel off the m's. We don't have to because I gave you what the mass was, but we can cancel them off. Okay, and I'm looking again for hi. So I want to subtract the 1/2 vi over to this side. Okay, and that'll leave me with g times h. Divide both sides by g, and I've got h. Okay, so hi will be 9.81 times 10 plus 1/2 times 16 squared minus 1/2 times 4 squared divided by 9.81. So 9.81 times 10 plus 0.5 times 16 squared minus 0.5 times 4 squared divided by 9.81. All right, so we're looking at a height of 22 meters. for our initial height. All right.
There are other questions like this, whatever's on the bottom doesn't cancel out what's on the top, because the top and the bottom are both separate expressions.
Right, you mean the 9.81?
Yes.
Yes, because this is, yeah, you're right, it's a separate operation. Yeah, exactly. Okay, what else, guys? Okay, well, I'll give you guys a little bit of time to maybe work through the review package. There are a number of questions from Unit 2 in the review package. Maybe we'll need some help with those. So we'll give you a few minutes to get to work on those and see how you do. Or work on some stuff from Unit 2, look at your worksheets or your assignments or something like that. See if anything looks like you might want to ask about it, okay, for the test, right? And just ask, and we'll answer. Okay, so for this question here, okay, we're going to start out with that we have to put in basically all the other forces that are acting. Okay, yes, the tow truck is pulling at an angle with 3,000 newtons. The car's not going that way. So what we need to do is break this up into the vertical component of that 3,000 and the horizontal component of that 3,000, because the vertical component is going to affect how much friction is experienced by the car. Okay, part of its weight is being supported by the tow truck. So not all of its normal force, is not equal to the force of gravity. And we need that normal force to calculate the force of friction. All right, so we know that there is a force of friction acting backwards because they told us that mu was 0.3. Okay, the other forces that are involved are the force of gravity, okay, which is 9,810 newtons. Okay, and then we've got to calculate these two parts here. All right, so my force vertical is going to be the sine of 20 times 3,000. Okay, so the upwards force is 1,026 newtons. I'll keep all the decimals when I do the calculation later. Okay, so that equals my force vertical. Then I'm going to have a normal force that's obviously a lot greater than that, but because I did such a crappy job with scale, it doesn't look that way. Okay, all right, how do I get this normal force? Well, I have to subtract how much weight is being supported by the truck from the actual weight of the car. Okay, so I'm going to do that next. 9,810, okay, minus my answer from the last one, right, gives me a normal force of 8,783.9 newtons. Okay, now I've got that. That can help me calculate the force of friction. Okay, everybody with me so far? Okay, so that can help me calculate the force of friction using the formula for FF. That's mu times the normal force, okay, which is simply going to be 0.3 times that 8783.9. Okay, so times 0.3. I went divided. Okay, let's do that again. That times 0.3. All right, so 2,635 newtons. Obviously, I'm keeping all the decimals, okay, but that's my backwards force. Now, I don't need any of these other forces except for the one I haven't calculated yet, and that's my force horizontal. Okay, I've used all the other ones to get what I needed. I needed all of those other forces just to get the force of friction. Okay, roundabout way, but the only way, okay, to get it. So now that I've got those, I need to figure out how much force is pulling the car forwards. Hopefully I haven't screwed this question up too badly and it's not less than this number. Because I did that this morning with one of the questions that we did, and it said that friction was going to pull the car backwards at like a significant rate of acceleration. Okay, so hopefully I haven't done that. Okay, 3,000, so we'll go cos of 20 here because we're looking for the adjacent side, times 3,000. Ooh, it's close though. Okay, 2,819 newtons. Okay, so we don't have a very big acceleration here. What do I calculate next? F net. Okay, everything else is taken care of. Upwards forces and downwards forces cancel because the car's not moving vertically. So F net equals 2,819 minus the 2,635. Okay, obviously we'll keep all the decimals when we do that calculation. So that subtract that number gives me 183.89 newtons. All right, so. And that's forward. Question didn't want the net force. Question wanted the acceleration. What do I do with that number? Divide it by m. So I divide that by 1,000, and I find that my acceleration is 0.18 meters per second squared forward. Because I only have 2 significant figures in that question. Okay? That would be about as tough as they would get. But it does involve everything from that unit. It involves net force, it involves friction, it involves vectors, okay? So yeah, it's a good question, and I can test a lot of concepts in one question, okay? I can also do that with an inclined plane, which we already went over. What else? So box is being pulled up this hill, okay? Constant velocity. That doesn't matter. We're never going to use that. Okay, all we need to know is that it's a constant velocity, so we know the acceleration and net force are 0. Okay, so what we have to do is identify all the forces. We've got a force of friction of 60 newtons acting down the ramp. We'll have an F parallel as well. Okay, we don't know what it is yet because we haven't calculated it. Come on, go away. No point. Okay, so we've got to calculate our F parallel, same as we always do. Okay, so this side's FG, and that'll be 98.1 newtons. Okay, this side here will be F parallel, which we'll calculate by going sine of 20 degrees times 98.1. Okay, so that'll be 33.55. Alright, so 33.55 newtons, okay, is our F parallel. That's not to scale, then obviously that line should not be longer. Alright, that means that our up the hill force must be 94 newtons. We only have 2 significant figures here, so 94 newtons up the hill for our applied force because our net force is 0. Okay. All right, what else? Conservation of energy. Got one for that too. Okay, there's your conservation of energy question. Okay.
Never mind. Take it back.
10 kilogram thing at the top of a frictionless thing.
Wow.
Incline, yeah. Okay, top of a frictionless incline. Okay, we don't know how high it is, but we know it's moving at 4 meters per second. A little while later, not long. Okay, it's 10 meters above the bottom, moving at 16 meters per second. Calculate the initial height of the box. Down.
Okay.
That's why it says F at the bottom.
Oh, right.
So final, F for final. Yes, I can please pause the recording since I'm making